This is our first set of guided notes, Unit 1 guided notes, and in these guided notes we are going to cover valid measurements, density, and atomic structure. Always at the start of a set of guided notes you'll see an introduction of some sort. Please take some time to read out this introduction. It gives you the big picture of what this unit entails. And it also has some key vocabulary words and definitions to help us to understand this unit. So please go ahead and read this, understand it, and we will proceed from here. When it comes to these guided notes, please make sure that you're really reading it in chunks. It's a long set of guided notes of a long video, so please make sure you take your time and kind of chunk it, understand it, and then move on to the next chunk. Pace yourself through it, especially when I assign homework. We're going to begin this unit with scientific notation, a little math review for us. Scientific notation is oftentimes used to write very large numbers as well as very small numbers. The format for scientific notation is always n times 10 to some x power. Now, as we look at this format, n is always between 1 and 10, can be equal to 1, but never equal to 10. So it always is less than 10 as a value, but it has to be greater than 1 as well. So let's move to the next page. In scientific notation, the exponent x is going to be positive because your number in standard notation was greater than 1. So let's look at this set of examples. We'll look in A, we'll notice that this number is greater than 1. So our exponent should be expected to be positive. So it's 9.8. This number, notice how 9.8 is between 1 and 10 times 10 to the 0 power. Now 10 to the 0 is really 1, and 1 times 9.8 is still equivalent to 9.8. So your scientific notated number should not have a different equivalent value, mathematical equivalent value. So let's look at the next one, B. In letter B, we're going to put the point right between the 2 and the 3. And we're going to include all the digits up until the last non-zero digit, which is 1. And then the exponent is going to be a positive exponent. And how I'm going to determine what power of 10 is I look at where I put the decimal between the 2 and the 3. And I look at what the value of the number is. The decimal point value-wise is at the very end right there. And I count my way from this decimal point all the way to this decimal point at the end. And it looks like it is 7 powers of 10. 3 here plus another 3 plus 1 here. So 7 powers of 10 means just that. It's 10 to the 7th power. Moving on to exponents where you see a negative because your number in standard notation was less than 1. Notice how this number is less than 1. And it's a very small number, so we're going to see a negative exponent. So let's start off with putting our numerical value. I'm going to put the decimal between the 4 and the 0 and add all the non-zero digits past that point. Times it by, well, the decimal point is where I put right here between the 4 and the 0, and then I have to count my way where the original decimal point is, and when I see that's however many powers of 10, so I have to count very carefully. I'm going to do 3 at a time. It looks like it's 9th, so it's 10 to the negative 9th. Same with over here, I put 7.650. I'm putting the decimal place right here, and how many powers of 10 between this original decimal point and the one that I put in, and it looks like it's 3 powers of 10, so times it by 10 to the negative 3rd. So I'd like you to take some time and make sure you read up on this information. Make sure you're moving powers of 10, whether you're dividing or multiplying by powers of 10. And then go ahead and work through these example problems. I'd like you to pause right now so that you can work through them correctly, put them all in proper scientific notation, and then check your answers. The metric system. The metric system is a part of Le Système International du Unités. It's a French word. And so it's called the SI system. And it's a measuring system that's agreed upon among all the scientists around the world since the 1960s. And we like the system because it involves powers of 10, movements of powers of 10. And there's 6 prefixes that we will really concentrate on in our class. And the prefixes are listed down here. It goes all the way from king, kilo to milli, milk. So I have a mnemonic to help us to familiarize ourselves. King Henry died by drinking chocolate milk. And this is a very common part of the unit that we will explore moving forward. But before we do that, let's talk about the SI system for measuring length, which is meters, mass, grams, time, seconds, volume, liters, temperature is in Kelvin units, and energy is in joules. These units are your base unit, which is right here, the base unit. And then there are prefixes that go in front of those base units that we can convert between. So let's go ahead and look at this first example problem down below here. We're converting 5.6 meters to millimeters. So I look up here and I see that I am currently at 5.56 meters is the base unit, and I'm going to milli, which is over here. How many powers of 10 am I going to move? Well, if I'm moving to the right, I'm multiplying it by powers of 10. If I'm moving it left, I'm making it into a bigger unit, which means I'm dividing it by powers of 10. So move to the right, multiply by powers of 10. Move to the left, divide by powers of 10. And so we're going to see that actually down here when we move, okay? So going from the base unit, meters, to milli is 1, 2, 3, 3 powers of 10. So I'm going to take my decimal and move 3 powers of 10, which is 1, 2, 3. Notice I stop at the very end here because my final decimal point is at the very end, which means I end up with 5,600 with the dot at the end right there. That's where my decimal point landed. And so what I've done is I've taken my number, and each time I move a power of 10, I'm multiplying by a power of 10. Moving another power of 10, multiplying by another power of 10, moving a power of 10, multiplying by a power of 10. Ultimately, I am multiplying it by 1,000 because 10 to the third is 1,000. And that's what you're seeing. When you take 5.6 and you multiply this by 1,000, you get 5,600. Let's go the reverse direction. Now I have this number right here. It's 5.6 meters, and I'm going to kilometers. So I'm going from meters to kilometers. And that looks like I'm moving 3 powers of 10 from base unit to kilometers. Notice the 3 spaces I'm moving, and thus you're going to see me move 3 spaces over to the left. And now, because I'm moving to the left, I'm making it into a smaller number, which means I'm dividing it by powers of 10. And I'm dividing it by 3 powers of 10, which is 1,000. So really, when I take 5.6 and divide it by 1,000, I will get 0.0056. And of course, I should always write the units. This is millimeters and this is kilometers. Hope you know that metric system is a very simplified system that works off of powers of 10. And that's why we really like using it among the scientific community, because of how easy it is to use. I'd like you now to go ahead and go over and work through some of these problems. Once again, the answer key is right here. Pause if you need to in order to work on those problems, and then we'll move on to sig figs afterwards. in this topic of significant figures, we're really going to answer this rhetorical question. How good are measurements? There are two words we use to describe our measurements. The word are accuracy and precision. Most people use these words interchangeably without understanding that they have different meanings. The word accuracy is how close the measurement is to the true value or the literature value. Precision is how well can the measurement be repeated. So let's look at these examples to see how we use the word accurate and the word precise. So here's a dartboard. Yes, you are looking at a dartboard with darts on the results of a sample of darts. And so the question is this student accurate? Now, accuracy is defined as being right in this shaded hole right here, within this shaded hole. Precise is probably is within an area together, okay? So precise is repeatability, just a reminder. So is this student accurate? Notice the student did not hit the hole, so I would say it's not accurate. But are they precise? So notice that they are on basically repeating their measurements in the same location, even if they're not accurate. They are precise in the sense that they are repeating their same measurements here. So I would say that they're precise. Now let's go to the second example. In the second example, you'll notice that they are within the same area. Not only that, but they're also in that bullseye, which means not only are they accurate, but they're also precise. Let's look at the third example. Notice how each of the darts are all over the map, in different places. So they didn't repeat themselves very well, but they did have one dart that was in the bullseye. So I would say it only takes one measurement to really say that you're accurate. And so I would say that they're accurate, but they are not precise in this example. So we see all different varieties of samples in these dartboards of how the word accurate and precise can be differentiated. So let's go ahead and go over some rules for significant figures. In significant figures, there's a couple of things we have to understand before we start off. And the words are leading zeros, as well as trailing zeros and captured zeros. Leading zeros are zeros before the first non-zero digit. So if my first non-zero digit is 4, as I see here, zeros before that is considered a leading zero. Zeros that are captured are between two non-zero digits, like you see here. So these are captured zeros, just like the word captured, between non-zero digits. Trailing is a zero at the end of the last non-zero digit. Now we're learning zeros because there are some rules that are revolving around significant figures with those zeros, okay? So let's start off with the first set of rules. All non-zero digits are significant. So we're going to see in this first example that we see all of these digits right here are all non-zero, and thus they're considered significant. So we count how many significant figures we have. We see 1, 2, and 3. So 3, and I'm going to abbreviate significant figures with the word SF. B. Notice how all those digits are non-zero digits. And so there's 1, 2, 3, 4, 5. There are 5 non-zero digits. So there's 5 significant figures. Lastly, there's 2, 4, 6. It looks like 6 significant figures there. So that's the first rule. Now we go to rule number 2. Number 2 states that leading zeros are not significant. And that's why we had to understand what leading zeros are from the top. Leading zeros are basically the zeros before the first non-zero digit. So they're not significant. So you can't count them as a significant figure. So let's go ahead and look at the first one. It looks like these two are leading zeros. They're not significant. That means the other non-zero digits are significant, as we learned earlier as the first set of rules. So there are only 2 sig figs in A. Here we see a bunch of leading zeros. So all of these digits right before the 1 are leading zeros. And so there should be only one significant figure, which is the number 1. That's the only significant digit there. Then we go to the next one. A lot of leading zeros before the 1. So it looks like 1, 2, and 5 are the only sig figs, and so there are 3 significant figures. Now we get into the third rule. The third rule says captured zeros are significant, so we have to count them. Captured zeros do count. And so we see that this 0 right here between the 4 and the 8 are captured. The 0 right here between the 8 and the 2 are also captured. So there are 6 captured zeros. Oh, sorry. 6 significant figures, including the 2 captured zeros. My apologies. Now we go to the next one. In letter B, here's a captured 0. Even if there's a decimal point, it's still captured between the 3 and the 9. Here is another captured 0 between the 1 and the 1. And so that's counted. And all the non-zero digits are also counted. So there is 2, 4, 6, 7. There are 7 significant figures. And lastly, we see a combination of some captured zeros as well as leading zeros. We know leading zeros do not count, but captured zeros do. And we do know the 6 and the 1 count for significant figures. So it looks like we have 1, 2, 3, 4 significant figures. Let's go to rule number 4. Rule number 4 says that trailing zeros are not significant unless it's a decimal point. So trailing zeros, remember, are the zeros behind the last significant digit, the last non-zero digit. So this is a trailing 0 right here. Now, do you see a decimal point anywhere in this number? You don't. And so the significant digits are these, all of these, including the captured zeros. And so there are 5 significant figure there. Now, unlike that scenario, let's look at the bottom, or let's look at B. In letter B, you'll notice that we have a decimal point here. So this trailing 0 is going to count. And that means we have 6 significant figures. So having that decimal point at the end really changes up the number of significant digits. And what really essentially means, if you're going, why does it really count, is because we must have measured to this decimal place right here. And that measurement is important. And so that's why that decimal point is going to say that that 0 is important. And so that's why it counts as a significant figure. It's all because we measured to that decimal place. Now we look over here. In this next one, we see a trailing 0 right here. And so all the 2 digits, 4 and 5, do count. And so we have 3 significant figures. Moving down to the bottom, we see leading zeros, captured zeros, and trailing zeros. Now, because there's a decimal point, that trailing 0 will count. The captured 0 always counts. Leading zeros do not count. So we have 2, 4, 6. We have 6 significant figures. I'm going to clean that up a little bit. Okay, now we go to the next. In the next one, we see that there's a leading 0, captured 0, and trailing 0. And because there's a decimal point, that trailing 0 will count. Captured always counts. Leading do not count. So in counting, there's 6 significant figures there. And then the last one, we see trailing zeros. So here's your trailing zeros. And then so that means, and there's a decimal point, which means those trailing zeros will count, leaving us with 3 sig figs. The next rule is quite easy. Rule number 5, all digits all digits in proper scientific notation are significant. And the digits we're talking about is right before it's the n, basically. So it's this n right here. They will always count as significant. However many there are, they will count, of course, following the prior rules as well. So it looks like I have 3 significant figures. I have B4 significant figures. So all of those significant figures, including the captured zeros, count. Here, I follow the rules. I still follow the rules. Notice how the trailing zero, this trailing zero right here, isn't going to count because there's no decimal point at the end. But this captured zero counts and all the other non-zero digits count. So there's 1, 2, 3, and 4. There's 4 significant figures. Over here, we see trailing zeros, yes, do count because there's a decimal point. Leading zeros don't, so I see 1, 2, 3, 4, and 5. I see 5 significant figures. Now notice in this example, you'll notice there's a trailing zero or a decimal point, and so these trailing zeros do count, which means they have to be counted in the significant figures, and so that's 4 significant figures. And last but not least, these leading zeros do not count. These trailing zeros do because of this decimal point, leading us with 3 significant figures. I would now like you to practice these problems. Use with this set of problems right down here, and again, check with the answer key. So go ahead and pause so that you can work through those problems. So there are some rules to addition, subtraction with significant figures, and that's what we're going to do. We're going to go through today. When it comes to adding and subtracting, your answer cannot be better than your worst estimate. That actually makes sense. Where if you've heard, you can only be as good as your worst player as a team. That's kind of like following the same kind of motto here. So if you look at your measurements, whatever your measurements that you're adding together, you've got to go by your worst estimate out of the two. So your final sum cannot be any better than your least decimal place or least precise of your measurements. So we start off by adding. When you add these numbers, you line it up. You actually can tell which one is least significant or at least your worst estimate. You can tell because they have the least decimal place. So this 6.4 goes only to the 10th place. The 4 stops. The 4 is the last digit and it stops at the 10th place. Whereas 27.93 stops at the 100th place. And so this is 6.4 is going to be the worst estimate because it has the least decimal place. So upon adding them together, even though they add up to 34.33 precisely, we do round it to the worst estimate, which is we're going to write 34.3 because our worst estimate is to the 10th place. So we rounded to the 10th place. Remember, recall your decimal places, okay? Please make sure you know your decimal places pretty well. And so I'm going to just do a quick review of your decimal places. That way you have an understanding of it. I'm going to do some numbers and digits. Okay, so I'm not going to do all of it. It's too extensive to do all. So I'm going to just go over some of them. This is called the thousands. This is called the hundreds. This is called the tens. And this is called the ones. So I kind of hit the top. Let's go to the bottom here. This is called the tenths. And it has a TH ending S. This next one is called the hundredths. So it kind of goes backwards with the THS. And then this is called the thousandths. The 4 is the thousandths place. And then the next one after that is the 10,000ths. And then the 6 is the hundred thousandths. We don't usually see it going all the way down there, but just know that the more the more precise you are, the better your estimate is it's going to go further out this way. So if you have a number that is 1,000.2 versus 1,000.234, you're going to see the number with the 1,000.234, because it goes further out in the decimal place, is more precise, is a better estimate. So when you do these problems, you want to work through and just make sure you practice rounding your numbers to that least decimal place. So I'm going to show you the first example because having one isn't enough. So I'm going to line up these two numbers. I kind of have to line it up to see who has the least decimal place. I actually can see it even before that, but so I add these two numbers. Upon adding these two numbers, my worst estimate is 4.8. So this is my worst estimate. And that 8 is in the tenths place. So when I add these two numbers, and upon adding them on my calculator, by the way, you can have your calculator for these calculations. I don't expect you to be adding and subtracting a bunch of numbers in your head. You get 11.6765 on the calculator. Now, it looks like I'm going to have to round it, and I'm going to round it to the tenths place. So it's going to be approximately 11.7 as a result, based on the worst estimate, which is this guy right here. Go ahead and work through these problems. Take a calculator out and start subtracting them, and please check your answers with down below. I make those answers very quickly accessible so that you can check them as you go. Now here comes the rules for multiplication and division with sig figs. When you round your quotient or your product, you want to make sure they have the same number of sig figs as the least significant figure. So in other words, if you multiply these two numbers right here, as you see happening, when you multiply them, you count how many sig figs each of these measurements have. And this one has 3, this one has 2, and so your final answer is going to be only as good as your least significant figure. So this number, this measurement, since it has 2 sig figs, my answer is going to have 2 sig figs as well. So I have to round it to 2400 in the end, this final product. Go ahead and work through some more problems. I'll do one more as a way to help you to ensure that you're understanding it. And so in this first example problem, you see that there is 2 sig figs. This measurement has 4 sig figs. And so I know that when I divide these two numbers, my answer, my quotient, is going to be rounded to 2 sig figs. So upon dividing them, and I'm going to go ahead and do that in my calculator right now. I get this really long answer, and the answer I get is 0.720576461. And I don't know where to, of course I can't keep that answer. I can only be as good as my least significant, the number that has the least significant figures. So since I have 2 sig figs in 4.5, I'm going to round my number to 2 sig figs. And so those are my first 2 sig figs going from left to right, and so my answer is going to be 0.72. As easy as that. So go ahead and work through all of your calculations and practice problems all the way to letter H. And then there's some mixed problems. I'm going to do the first one so that you can see how I would go about doing it. Don't forget something called Pemdas, which is parentheses, exponent, multiplication, division, addition, subtraction. parentheses, exponent, multiplication, division, addition, subtraction. So here we have, in this problem, we've got addition and division. According to Pemdas, if we don't have exponents or parentheses to deal with, we do multiplication division first. So we're going to divide these two numbers first, and then we're going to add them afterwards, just like you see in this order. So first divide. Now, upon dividing those two numbers, you'll notice you have to use your division rule. And the division rule says that if this is 2 sig figs, and this number has 4 sig figs, your final answer at that point is going to be 2 sig figs. So when you take 0.2 and divide it by 6.245, you keep note that you want that number, which I'm going to write down. You want 3.3, oh sorry, 0.0 0.0320, and it's a long set of numbers, but I'm not going to write it all. But ultimately, you want to keep it at 2 sig figs here. Now, so you know your answer has to be 2 sig figs, just like 0.20 has. And then what you're going to do, now I'm not going to round it yet. I'm not going to round it until I finally take that number, the full number, and add it to 1.5. So I'm going to add those 2 digits. Now upon adding those 2 digits, you'll notice that because the significant digits are up to the thousands place right here for 0.032, the last significant digit is in the tenths place. So when I add these two numbers, I'm going to only round it to the tenths place because 1.5 has the least precise measurement. So it's the worst estimate. I'm going to write that down, worst estimate. And so I'm going to add in my calculator, by the way, you can use your calculator through this, you're going to see that it's 1.532, and it goes really long, but ultimately you're going to round it to 1.5 in the end. And treat every problem just like that, where you're just adding and making sure you take note of your sig figs. Let's do another one. These problems, mixed problems with mixed operations, can be very challenging. So let's look at B. In B, since there's parentheses, you add up these 3 numbers first, and you take note of the last decimal place that's significant. So the ones place right here, the hundredths place here, and then only the tens place here, because the 0 is a trailing 0 that's not significant unless there's a decimal point, and there's no decimal point. So the 5, this last 5, the tenths place is the last significant digit. So I'm going to take my calculator and add those 3 numbers. Upon adding those 3 numbers, I'm going to note where my last significant digit figure, or the decimal place is my last significant figure, okay? So upon adding that, I actually get, and I'm going to write it on the side, 5087.9. Now, I know that the worst estimate out of all these 3 numbers is in fact the 550, because the 5 right here is in the tens place. So I know, and I'm going to make mark, that the tens place is my last significant figure. So I'm going to put 3 arrows to list those 3 significant figures. And of course, my last significant figure is right here, which is in the tens place, just like that 5. And so now I'm going to divide. Notice I leave the number at whole. I'm going to divide this whole number by 3. So I leave it in my calculator as what it is. I'm not going to round it until the very end. And then I divide it by 3. And upon dividing it by 3, I notice that 3 only has 1 sig fig. And I noticed that I have 3 significant figures here from my last operation. And so my answer is going to be 1 sig fig. And that ends up being, so the answer is 1,695 or 96 if you, or 0.9. Okay, let's put another digit. But ultimately, I only should have 1 sig fig. And so it looks like I'm going to round up to be 2,000. Okay, and you can put a parentheses if you want or not. I'm going to do another one. I will need a little room, so I'm going to erase this part right here. And that will give me some room through my calculations. Don't know why it's not erasing, but there. It was getting a little messy there. All right, so looking at the next number we're subtracting. So in parentheses, taking those 2 digits and subtracting. And I'm going to note the least significant decimal, or the least decimal place, okay? So in other words, I'm going to check these 2 numbers out, and it looks like this number has the least decimal place because it goes to the hundredths, whereas this one, the last significant figure, goes out to the thousandths. So when I subtract these 2 numbers, I know my final answer, or my final difference, is going to be to the thousand or hundredths place. So 1.367 minus, in your calculator, go ahead and punch that through. And so I get this number. I'm going to work it up on top here so you can see. I get 0.027. And then I note where my sig fig should be, and I know it's going to be in the hundredths place. So I put my arrow to the last significant digit, or however many significant digits leading to the hundredths place. So that's my hundredths place right there. And that's the only significant digit because, remember, your leading zeros are not significant, okay? These 2 leading zeros. All right, and then now I have to do my next function. My next function is to divide this by 2.0, and upon dividing it by 2.0, I have to count sig figs. And counting my sig figs, I'll make it a different color so we can see. This is 1 sig fig because I noted that this was my my only significant digit in the tenths place. And then this one, this number, has 2 sig figs. So my answer has got to be 1 sig fig when I divide these 2 numbers. So dividing it by 2, I get as my final answer 0.01. And you should see it in the, I edited the key, it's 0.01. Okay, go ahead and finish up the problems. We're moving on to density. So density is, by definition, the mass of a substance per unit volume. Per unit volume. And so that's exactly what you see as the units. You'll see the units to be mass per unit volume. So mass, grams per milliliters, grams per cubic centimeters, or grams per liter. So how does a boat that weighs 1,000 kilograms, which is really 2,240 pounds, stay afloat in the ocean, or on the ocean? Mass is not the only variable in determining whether a boat will sink or float. Volume is important as well. So the density relative to its surrounding liquid would determine whether the object will sink or float. While the boat is quite massive, the volume is so much larger than the mass of the boat, making it less dense. And this is what I like to normally do. I like to see the ratio relationship. So density is mass divided by volume. If you have a high amount of volume, which is in the denominator here, you're going to see this ratio go down. And that's precisely what you're seeing in a boat. A boat, though it's massive, has a lot of volume, much more volume than the mass, such that the density is less than 1 and will float compared to the salt water that surrounds it. So here is the equation for density, and we're just going to work through some problems as far as density is concerned. Now, I like modeling as a way to help us to understand. So this rock must be more dense than the surrounding liquid, which is water. Water's density is 1, so this rock must have a density greater than 1 in the end. So let's go ahead and go through example 1. A cylinder has a mass and a density of the following. So mass of 550 grams and a density of 2.70 grams per milliliter. What is the volume? So we're looking for volume. And when it comes to a word problem, what I like to do is just underline the information that's important, and then I start substituting it into the equation that is relevant. And density is the equation that I am focused on. So I'm going to substitute 2.70 for D, 550.0 grams for M, mass, and then volume is what I'm looking for, so that will be my unknown variable. So substituting everything in, 2.70 equals 550.0 grams. And then volume is my unknown variable. I like to use x as my unknown variable. So upon solving for x, I get, so essentially what I'm going to do is cross multiply or switch these two guys, switch these two places, because that's why cross multiplication works, is because you can switch those places. So now I get x equaling 550 divided by 2.7. And my answer ends up being 204. And then I am going to sig fig it and make sure I sig fig it. So my numbers sig fig wise are the following. I have 3 sig figs here, and then I have 4 sig figs. And notice my answer is going to be 3 sig figs in the end, and that's precisely what I have, 3 sig figs. So I should sig fig all along the way. I'd like you to work through the second problem and make sure you see what should happen to that rock when you work through the second problem, okay? Again, rock. If the rock is more denser than the liquid, water's density is 1 gram per 1 milliliter, you'll see that it will sink. If it's less dense, then it will float in the end. Okay, let's get into atomic structure. Now, a chemist is oftentimes very interested in the reactivity of a reaction. And the reactivity depends on the atom's ability to gain or lose electrons. And so that's why atomic structure, this whole idea of atomic structure, is a very important part of laying down the groundwork for a chemical reaction and the reactivity. In an atom, there's positive charged protons in the nucleus that attracts the electrons, while the protons repel other protons, and of course electrons do the same with other electrons. The reactivity of atoms depend on the structure of the atom and is governed by something called Coulomb's law. Coulomb's law is very important, and Coulomb's law is the mathematical model describing those attractive forces and repulsion between the objects. And of course, it depends on 2 ideas, charge and distance. So let's go ahead and look at this equation. This is the Coulomb's equation right here. K is a constant. You don't need to worry about that constant because you'll never be given anything to solve for this equation per se. You'll do it in probably physics. But in chem, you're just understanding what this law entails and how to manipulate the concept of it, okay? So Q represents the object, the charge of object 1 and object 2. And then D represents the distance between the objects. So if I have higher charge, I get higher force. If I have higher distance, they're farther apart, there's less force. That makes sense. If 2 particles are farther apart from each other, they are going to be less attracted to each other. There's less force applied upon each other. So, as the charges of each object increases, the force between the objects increases as well. That means charge and force are directly proportional. Once again, you see the equation that I like to put into understanding. If Q increases, you know force increases as well. So they're directly proportional. The charge in an atom is really focused on the core charge, which is the charge of the protons inside the nucleus and its effects on the valence electrons, which is on the outside of the atom. We call this effect. This charge, the nuclear charge's effect, the effect of nuclear charge, which makes complete sense as far as the name itself. Now we denote it in a symbol. It's called Zeph. We call this Zeph. To calculate Zeph, we take the number of protons minus the inner shell electrons, just like you see this equation right here. And again, it measures core charge. Now, let's go ahead and refer to below, which is refer to both models below, which atom, B or F, has a stronger force. And so notice if you look at both models, they both have the same number of rings here, or shells, and they both have 2 shells. So the distance doesn't seem very far, or the distance doesn't seem very different between the two, because they both have the same number of energy levels. But what is different is the number of protons. So if you see between beryllium and fluorine, which is Be and F here, one has greater number of protons, and that's F. Because it has a greater number of protons, you're going to see the nuclear charge be so strong that it will draw the valence electrons as well as the inner shell electrons a little bit more in. And because of that, between the two atoms, you're going to see that fluorine has a stronger force. So I'll write that down. Oops. Fluorine has stronger force. And how we justify it is through the Zeph calculation. So let's go ahead and use evidence. Evidence is through this lovely equation and calculation for this equation. So let's go ahead and do that. Zeph for beryllium, so Z for Be, is calculated by taking the number of protons, which is 4. There are 4 protons in the center here. And then we're going to subtract the inner shell electrons. And the inner shell electrons, if you count very carefully, this is in the inside. These are valence electrons, and these are the inner shell electrons. There's only 2. So 4 minus 2 gives us a Zeph of positive, or you don't need to have that positive. Just call it 2. So just say 2. Okay. The Zeph for fluorine is calculated the same way. 9 protons minus 2 inner shell electrons and 7. So who has a higher core charge? And it looks like, of course, fluorine has a higher force because it has a higher core charge in the end. Okay? So we can say that in the end, fluorine has a stronger force than beryllium because fluorine has a higher core charge. And you want to mention the word charge, and that's because this equation is all centered. Force and charge are directly related to each other. Now we go into the possibility of distance. So as the distance between objects increases, the force between the objects gets weaker. Distance and force are inversely or indirectly proportional. The distance in an atom is primarily focused on the energy levels in an atom, thus we label this the principal quantum number. N can be determined by the atom's placement on the periodic table of elements. So I'll need you to get out your periodic table of elements so we can begin the next phase of seeing how distance and force interact. When an atom, if you look at an atom's placement on the periodic table, you'll notice that if you are on the first row, the n equals 1. On your periodic table, it's labeled n equals 1, and that's the principal quantum number, which is the energy level. And so notice there's only one ring for each of these atoms because they only have one energy level. Now we go to the second energy level on the periodic table. Notice they have 2 rings, and thus they have n equals 2, which is the highest principal quantum number. Third row here has 3 rings or 3 energy levels. So you can actually look at the periodic table and determine the energy levels by the rings. And it actually is denoted on your periodic table, so I hope you pull it out because you're going to need it as you go through this. Now we refer to both models. Which atom, beryllium or magnesium, has a stronger force? So immediately you see different number of rings here. Beryllium has n equals 2, whereas magnesium has n equals 3. And because beryllium and magnesium has a longer distance between the nucleus and its valence electron, which is right here, that means its force is weaker. It has a weaker force. Whereas this one, beryllium, has a shorter distance, so they have a greater attraction. So the one that has the stronger force is going to be beryllium. Beryllium has a stronger force because it has a shorter distance. And I'm going to just label force. Because it has a shorter distance, it has only 2 rings compared to the 3 rings that magnesium has. So this is magnesium on this side. So use Coulomb's law with respect to either shorter distance to explain why the force is stronger, or in the previous example, the stronger charge to explain why the force is stronger. Okay, now let's go ahead and go into parts of an atom. So here you see the structure of an atom right here on the side. You've seen this structure before. An atom is often modeled with a nucleus full of protons and neutrons. And so the nucleus is the center of the atom with protons and neutrons. And then, of course, we have electrons floating around the electron cloud. Now, the force that holds the nucleus together is something called nuclear force. And then, of course, the force that's holding the electrons in an atom is called electrostatic attractive force. And let's move on to describing some of the properties of the subatomic particles, the electrons, protons, and neutrons. These are the symbolic representations of them. These are the charges of them, where they're located, and really, I really want to bring your attention to this. You don't have to memorize this, of course. Of course not, but you want to know relatively the masses. So if you look at this, electrons are very light in weight. They're 1/1840th of the weight of a proton or a neutron. Notice the proton and neutron have similar relative masses. And the way they did this mathematics is they divided by the lowest value, which is this right here. And so, divide both sides by each other, and you'll see this becomes 1. And then when you divide this by 9.11 times 10 to the negative 28 by 1.678 times 10 to the negative 24th, you'll get this number right here in the end. So ultimately, the takeaway from this is that the mass of an electron is very little compared to the mass of a proton and neutron. So that's why when you lose an electron in an atom, you won't see the masses or the mass of that atom or that ion significantly change compared to the neutral atom that it was before it lost an electron. So, what part of the atom accounts for most of the atomic mass? It's usually, obviously, these two right here because they're more massive, right? So, it's the proton and the neutron, which is located in the nucleus. So, where's the most dense part of the atom? Well, density, reminding us, is a ratio. Density is a ratio of mass over volume. So, most of the denses, or where it's most dense, is where you see most mass in the end. So where you see most mass is the nucleus. Where do you see it? What accounts for most of the volume of the atom? And of course, you'll notice that the electrons are moving spread out in the electron cloud, and that's where you're seeing most of the atom's volume in the end. Electrostatic attraction is a word and definition that I'd like to make sure you know because I'll use it quite often. It's basically the attractive forces between the electrons and protons, and then the repulsive forces also. So there's actually electrostatic attraction or electrostatic repulsion. And those are all forces, that are guided by Coulomb's law, which we covered already. Okay? What subatomic particles identify the identity of an atom? And that is the number of protons. And because the protons are well protected in the nucleus, and it doesn't ever change that number, we use the protons as a way to identify an element. Explain why not the other. Well, because protons or electrons can easily be lost or gained in what is called ions, we don't use that as an identity of an atom. Likewise, neutrons can also be changing in the same element, and that's called isotopes. And that's why we don't use those, because that number could be changing as well, for the same element. And so ultimately, the one and only particle in an atom that we identify an element by is the atomic number. An atomic number is like your social security number. The minute you're born with it, you're issued one, and then the minute you die, it goes with you. It never gets recycled through. So look at your new copy of your periodic table. Get yourself familiar with the key here, this little key legend. The top number is the atomic number, element symbol, element name, and then of course something called the average atomic mass. This mass actually represents the most stable isotope that you will discuss soon enough what an isotope is. So there's two types of symbols. There's something called the nuclear symbol, and there's also called the hyphen symbol. The nuclear symbol always has something where you have on the upper left-hand corner, on the left-hand side, a mass number, which is the number of protons and neutrons. There's also an atomic number, which is the number of protons, and then charge, which is the number of electrons. It describes the electrons that are lost. So if you look in this symbol right here, it actually integrates all three subatomic particles: the electrons, neutrons, protons, and of course protons again. Protons being very important to the identity of the atom. So that's why you're seeing it reiterated twice. So when you subtract the atomic number from the mass number, that's actually how you achieve the number of neutrons. And so that's why subtracting this number from here, you get the number of neutrons. Hyphen symbol. The hyphen symbol is the element name hyphen with the mass number. And once again, the mass number is the same number that you see over here, which is the number of protons plus neutrons. This is oftentimes used for isotopes in the end. All right, so let's go ahead and look at the symbols and the examples for each of the symbols. Here we have, once again, the nuclear symbol. You can see the similarity in the symbol, whereas the hyphen symbol, you can see there's a hyphen between the name of an element and a number of some sort, the mass number. Okay, looking over here, The top number is the mass number, which is the number of protons and neutrons. So, and the bottom number is the number of atomic number, which is the number of protons. So we can easily identify the number of these particles. Electrons are over here, okay? And I'll show you how to do each one. So starting off with the number of protons. Match directly right here. This is the number of protons, so it's 9. The number of neutrons is just subtracting the mass number or the atomic number from the mass number, and so that's 10. And so the answer is 10. Remember, you just have to subtract the atomic number from the mass number to get the neutrons. Electrons. To do electrons is to say to yourself, okay, normally 9 protons, positive charge, plus 9 electrons gives you a charge of 0. So that's what your charge would be if it was equal. So now what if 9 protons added to some number to equal -1, what would that some number be? It's got to be a -10. So the number of electrons is 10. So that's why you can get a charge overall that is -1, because there's one more electron than there is proton. One more electron than there is proton. So let's go ahead and finish this up. Atomic number is the 9 that we see. That's a reiteration of the number of protons. The mass number is written as 19, and then the average atomic mass is obtained always from the periodic table. So let's go to the periodic table, the one that was handed out to you, and please check to see what the average atomic mass is. And so in other words, go to your periodic table, find fluorine, and find this number that's underneath the element name. That is the average atomic mass. And if you write 19.00, that is correct. It's a little messy here. I tried to erase it. Could not. I don't know why. But there. So yes, this is 19.00. Okay. Now we'll jump over to the hyphen symbol, or also called the isotope symbol. So carbon, this number right here, 14, is really the mass number. It tells us the number of protons and neutrons. So where do we go to find the atomic number? Well, the atomic number is found on the periodic table above every element. So if we know this is carbon, we can look at carbon on the periodic table and look at the number above it. And that is the atomic number, which is the number of protons. And we see that in the end, I see the number 6 above the carbon. Okay? And then the number of neutrons is, again, taking 6 subtracted from 14, which is both protons and neutrons, will give us the number of neutrons. And that is 8. The number of electrons, because you don't see a charge, or it's not an ion, it doesn't say the word ion or anything on the word carbon, we can assume that the number of protons and electrons are equal. So it should have 6 electrons. The atomic number, once again, is just the number of protons. Mass number is 14. Average atomic mass is just a quick look on the periodic table to see what that number on the bottom below the element symbol is, or element name. And that is 12.01. So you'll need your periodic table out as we go through counting parts of an atom, protons, neutrons, electrons, and such, and working through the symbols, the hyphen as well as the nuclear symbol. So I have the key on the bottom. I really do want you to practice that bottom part with the key. I mean, the key is there, but I would like you all to practice on your own first before you do that. But let's go ahead and go through the first 2. They're empty so that you can work it through with me. Okay, so the nuclear symbol. Actually, let's go ahead and fill out the protons and electrons first. So I know that this is boron, so I look on the periodic table and I spot that it is boron. And boron has a atomic number of 5, and so I'm just going to put the protons, 5. Because I do not see charges on any of these, or boron, so in other words, I don't see any kind of suggestion of a charged particle. So again, I don't see any ions or anything to suggest it's an ion. I will assume that it's neutral, which means it's got 5 electrons. Average atomic mass is just a matter of looking at your periodic table and writing that number beneath the element name. And it looks like it's 10.81. And then mass number is basically the number of protons plus the neutrons. So protons right here plus the neutrons gives you 10. And that is always our mass number. Now we go into the atomic number. Atomic number is 5. The hyphen symbol is just saying, hey, it's boron. You can use the element symbol hyphen mass number, which is 10. And then the nuclear symbol is going to be B. And since it's neutral, you won't see any number. You won't see any number on the upper right hand corner here. So it's pretty much 0. And then the top number is always the mass number, and the bottom number is the atomic number. So this is the nuclear symbol. All right, let's go to the next one. Now, for this next one, I want you to note a couple things. It says right here that the mass number may assume the most abundant naturally occurring isotope. Most elements have multiple isotopes, and the one that is most abundant, and you'll understand more so when we get to the end of this set of notes, the one that's most abundant is going to be represented in the average mass. So if you look at this, since it's the average mass is 10.81, you can assume that probably the most abundant one is probably boron 11, because it's really close to 11 rather than 10. It wouldn't be boron 10 that's most abundant, okay? Likewise, if we go to this one, you'll see that the average mass is 22.99. It's really close to a whole number of 23. So we can assume if we're not given the number of neutrons, and we're not here, that the most abundant isotope is represented in this atom right here that we're working on. So that's why 23 is the one that we're focusing on, the isotope 23, or sodium, or sorry, didn't tell you it was sodium, but it's sodium 23, okay? Now, how do I know it's sodium? Because of the atomic number. I see that the atomic number is 11. I look on the periodic table and I find that identity of the element, and it looks like it's going to be sodium. So my symbol is Na for sodium. And sodium's number of protons is 11. Number of electrons, since it's a neutral atom, and oh, I forgot to point out that we're assuming all atoms are neutral. So they're always going to have the same number of electrons as the protons. The number of neutrons is just subtracting the number of protons from the mass number that we rounded off because we're assuming it's the most naturally occurring isotope. So when you subtract that from 11 from 23, you will get 12. And the hyphen symbol, I'm going to use the symbol instead this time so you can see the variations. So we put a hyphen there and the mass number, which is 23. So this is the specific isotope, sodium 23. Symbol is just Na 23 and 11. So that is the nuclear symbol. So now, please do not copy these problems and these answers. I want you to work through them and get your practice in. But the answer key is right here, and I wanted to leave it here so it'd be easier for you to track your answers for all these problems. Again, you're assuming they're always neutral, which means the electrons and the protons are equal all the time. And then you're assuming it's the most abundant isotope if they don't identify the actual isotope. And how you know they identify the actual isotope is they give you the number of neutrons. Okay? So otherwise you assume it's the most abundant isotope, which is taking the mass, the average atomic mass, and rounding it to the nearest whole number. Okay? So let's talk about isotopes. We're kind of doing a reverse on this, okay? Atoms of the same element that vary in the number of neutrons. And that's why if it's an isotope, all elements have several isotopes, and the most abundant, the one that's commonly out there, is going to be closest to the average mass because it's the most abundant one. And so atoms of a usually you'll see the same element, like you see here, carbon, carbon, carbon. But then what you see is a mass number that's different. Carbon 11, carbon 12, carbon 13, or carbon 14. And because they have different mass numbers, they must have different number of neutrons. The protons will stay the same because it's the same element. So since carbon has 6 protons, that means there must be 5 neutrons. 6 protons in this amount right here, the mass number, that means there's 6 neutrons. 6 protons subtracted from 13 gives you 7 neutrons. And again, 6 protons subtracted from 14 gives you 8 neutrons. So notice how they're all the same element with differing number of neutrons. Likewise, if you look at all four of these different isotopes for helium, helium 5, 6, 7, and 8, you'll notice they have different number, same number of protons always, same number of electrons too, because it's a neutral atom. Same number of electrons as protons, but what differs is the yellow balls, which are your neutrons. And so each one has a different number of neutrons, and thus they're isotopes. So I wanted to give you a visual model of how isotopes look compared to something that's just written out for you. So the average atomic mass, basically the number that's underneath the element name on your periodic table, is really a weighted average of all the naturally occurring isotopes for that element. And so, and of course, it's weighted by their percent abundance. We're going to learn how to calculate that in the next page. Units for average atomic mass is AMU. It's called atomic mass unit. And it's based off of carbon 12. We use that as the standard for 1 AMU. In other words, carbon 12, 1 AMU is a 12th of the mass of carbon 12. And so it's 1 proton. It's also equal to 1 proton or 1 neutron. Remember that protons and neutrons have the same masses. And so however many protons you have would be equal in mass for the number of neutrons. To calculate the average atomic mass requires a simple equation that we will manipulate, but you will have to understand this little summation symbol. It means sum. Sum means add. So you're going to multiply these different isotopes and their percent abundance, and then you're going to add them all together to get an average atomic mass. This is again the number underneath the element name on your periodic table. So a lot of times those numbers are going to be decimals, and the decimals because they're a weighted average. So let's go ahead and look at this really quick. Silicon has 3 naturally occurring isotopes. So this is your data set that's given to you. There's silicon 28, there's silicon 29, there's silicon 30. Now out of all 3 of them, their exact masses are given right here to them. Notice how they round to these whole numbers right here. So these are the mass numbers because they are rounded from the isotope mass. Now the percent abundance is given to us as well. We find this actually through using something called a mass spectrophotometer. We find out this data set from the mass spectrophotometer data. Now, with that data though, you understand that the abundance, silicon is the most abundant, silicon 28. And so you're going to notice that the average atomic mass is going to probably be closest to 28. So when we estimate, we're just going to give a number that we think it will be closest to. We're going to say it's closest to 28 AMU. We actually should calculate it as well, and that's what we're going to do using this equation on the top here, the average atomic mass. And so using that equation, it's an easy equation. The first thing you want to do is take your percentages and turn it into decimal form. And it's just to turn it into decimal form is to move it twice over to the left. And then you multiply the exact isotope mass to each of these, as you see right here. It's multiplied. The percent abundance is multiplied times the exact mass of the isotope. And that's, once I multiply each of those in my calculator, I am going to get several values. I'm going to get 25.80. And notice how big that number is, because the percent abundance is 92%, 92.21%, which means it's going to have a greater weight on the mass. So this is only small. It's 1.362. And then the last one is probably going to be small as well when we multiply by the isotope mass, the exact isotope mass. And it is small. So the contribution of all the numbers, the contribution of silicon 28 is the most because it has the highest abundance, whereas the other ones are less abundant, and so you're going to see it contribute less to the total mass. And so after this, you just add these numbers together, and upon adding these numbers together, you should, and you can actually check on the periodic table, get a number that is this. And check the periodic table. Check the periodic table, and you should see the average atomic mass to match up with this number right here. Okay? I'd like you to do example 2, and the answer key is exactly underneath, so you can actually identify an element from that, okay? Without knowing what element X is. So you have but this element X has 2 naturally occurring isotopes. You can kind of figure out an estimated value, put it like this is you estimating, and then you're actually calculating it as you go through this equation, okay?